Okay, so coming to examples on orthogonal trajectories, I'm considering here semicubical parabolas. How does semicubical parabolas look like? If you are aware of curve tracing, you will be knowing that the basic shape would be something like this. Okay, with the few checklists that we have in curve tracing, semicubical parabolas will look like this. Depending on the values of A, the shape will get changed. Again, this is a family, right? Yeah, coming to the solution. How do I do it? First thing is, since A is the parameter or the constant, I'll be eliminating the constant for which there's one constant, so I'll be differentiating. Consider ay square is equal to x cube. Let this be 1. Differentiating 1. Differentiating 1 with respect to x. So what I'll be having is a into a is a constant. 2 y square derivative is 2y. Y is assumed to be a function in x, so dy by dx. X cube is 3x squared. Okay. So what would be the value of a? A would be what? 3x squared by 2y into y prime. Okay. If I substitute the same thing in 1, let this be 2. 2 in 1. 2 in 1 gives me what? The value of a, because a has to be eliminated for a differential equation. 3x square y square by 2y into y prime. This is equal to x cube. This is y prime, guys. This is y prime. Okay. Yeah. Now, of course, I can cancel out one y from here, another from here. For the orthogonal trajectories, what am I supposed to be doing? For the orthogonal, you can just refer to the previous video. For the orthogonal trajectories, replace y with y prime. No, replace, I'm sorry, y prime with minus 1 by y prime or y dash, whatever. So what I'll have is 3x squared y by 2 into y prime is replaced by minus 1 by y prime. This is equal to x cube. Okay. Now, denominator by denominator goes to the numerator. So, I'll be having 3 by 2 separately. X square into y prime. This is equal to x cube. Guys, I can cancel out x square and x cube as well. I didn't notice it. Right. Now, 3 by 2 y into dy by dx. Actually, y prime is what? Dy by dx. This is equal to x. I think I can go with variable separable if you observe. So 3 by 2 3 can be put here. 3y dy. This is equal to 2x dx. Integrating on both sides, I'll be getting the solution. Integrating on both sides. Okay. What I will get is 3 integral y dy. This is equal to 2 integral x dx, which is nothing but 3y squared by 2. Of course, I have integrated. So, one time I have integrated and this is an indefinite integral. So, I should be inserting an integrating constant, arbitrary integrating constant. 2 into x squared by 2 plus c. Of course, here I can cancel out. Okay, I can as well rewrite this as, see, of course, just 1 second. I have missed out one minus sign here. Just a second. That is, here I have replaced y by minus y na. There I have, yeah, I have missed out a minus sign here. Okay. So there's a minus sign that's been carried out either for x or for y. Okay. Let's say it's there on the right only. It was there on left. It can be there on right. Now if I bring x square this side, I'll be having what? X square will be positive plus y square by y squared by, I can write it as 2 by 3 this is equal to C. And you observe, guys, if I see, actually this is my answer. What that is 3y squared by 2 is equal to minus x squared plus C is my answer. If I want to make it look little more better, I'm trying to do this arrangement. That is what? X square by C plus y square by 2 by 3c, this is equal to 1, which looks like an ellipse. Okay. Now I can say for the semi-cubical parabolas, ellipses are, this looks a bit like ellipse, guys, where I know my A and B, ellipse. So for the semi-cubical parabolas, ellipses are orthogonal trajectories. I can tell it in much refined manner, but that is fine. Even if you don't recognize that they are ellipses also, it is fine. Okay. So something like this, an ellipse comes depending on those things. Okay, so these ellipses become orthogonal trajectories to the semi-cubical parabolas. Okay, like that I can conclude. Otherwise, I can stop here saying this is the orthogonal trajectory for the given family of semi-cubical parabolas. Okay, yes. Let's do one more problem in the next lecture.